Hi everyone, are you excited? Woo! All right, I'm going to give 6 of these about testing. Given that I have 6 hours to talk, I'm going to start from scratch. Right. So suppose you just learned how to program. That's where we start, right? You've never written a test before. Why would you ever do it? So the first lecture would be, or the first thing, the first hour will be about why do you do this in the first place and how do we go about it. I have no slides for the first one. Let me just scroll down a bit. If I found the right button. Suddenly I forgot all the key bindings. All right, and then the second will be a standard example of what I call testing. No, you're not supposed to see anything. There are no slides at the moment, but the second hour there will be slides. For the second hour, there will be a standard example of what I call testing from first principles, and I think you'll enjoy that. And then I'll go into unit testing, property testing, how to do it in practice, like what you type. And then the third one will be about cheap property testing, so you can have property tests in 7 lines or less. And then I'd like to go over someone else's code, like someone from the audience probably has some code where they say, I don't know if this works, can we figure it out? And so I'll use someone else's code that I've never seen before and test it live. That's the idea. And then I have 2 more hours after that. We can either do more of that if it was fun, or I can start talking about other kinds of tests like golden tests and round trip tests and aggressive tests, and like there are 40 different kinds, so we have plenty of things to talk about. And then the last hour we can either do more of the live testing, or I can go through the procedure of regression testing, but we'll see that later. So if anyone has any suggestions of things to test, come talk to me after, all right? Cool, then I'm going to get started with the from scratch part. I've written down the outline here because it's important that I follow the right steps through this, so I'm going to be watching a bit. So why do we program in the first place? We're trying to make something happen, right? It's the closest thing that we have to actual magic, because you type in your spell and then something goes wrong, right? So you can actually, you have this wand in your pocket. Actually, I don't, because I have this recording thing. But you have this phone in your pocket, this wand, and you just wave it in the right way, and suddenly pizza appears. Like, that's magic to me. And so we try to make something happen. The problem is, as soon as you start programming, you notice it's not actually as easy as it should be. And you tend to do stuff wrong. So it turns out it's really hard for humans to do something right. And more important than to do things right is to figure out what right means. Software that you write will break. And it won't just break when you write it. It won't just be wrong when you write it. But it can actually become wrong after a while, either because you change your definition of what wrong means, or because someone changed something elsewhere, and it turns out your stuff starts breaking now. So I'm going to try to talk about what you can do to have any chance of making sure that what you wrote is doing the correct thing. Now, it's important to realize that there are trade-offs involved. So if you deal with $1 gajillion on a daily basis, then it's more important for your code to be correct, most likely, than if you're trying to have some little tool that says hi whenever you open your computer, right? You have to understand what it costs in real dollar value for your code to be wrong, or for human lives, or whichever metric you want to use. So you need to decide what amount of assurance you need that your code is correct in order to evaluate whether a certain way of making sure that your code is correct is appropriate for you. So keep in mind that there are trade-offs for all of these. So there are a few things we can do. The first thing you need to make sure you do is use the right tools. I was going to make stupid jokes about bad programming languages, but let's leave that out. So there are a few standard ways to make sure that by using the right tools, things are correct by the time you push them. The idea is to do something such that if it fails, you will have caught something that could have gone wrong if you actually try to run it. So you will perform some procedure, and if it succeeds, you are more assured that your code was actually correct. And so there are a few things that you can do. First of all, it's something I call pre-parsing. So that's where you parse the code that you just wrote before you actually run it to check that there are no syntax errors. There are languages where this already doesn't happen, like Python. There are other ways to actually use Python such that you actually do something that is equivalent to pre-parsing when it comes to syntactic correctness, but you get the idea. So the first thing you need to do is to make sure that your code is syntactically valid. There are more things that you can do at writing time to make sure that your code is more likely to be correct. The second thing is compiling. If the compiler fails, then it's not going to run, however hard you try. If it doesn't get compiled, it doesn't run. The third thing is type safety, and there are arguments to on both ends to argue whether that's a good thing, but there's no denying that something that's type safe is more likely to be correct. And then there are some, there are 50 more things I could be talking about here, but the right tools are important to make sure that the things you write are easily checkable for it's probably going to be wrong if these things fail. So there's parsing, compiling, type checking. Then there are a few more like formatting. Automated formatting makes certain things easier as well. So use the right tools. Once you've chosen the right tools, you can start to think about other things. If you're using JavaScript, start here. Don't start with the DevOps part yet. Make sure you use the right tools for your job. If JavaScript is the right tool, great, use JavaScript. But otherwise, please don't. Then there is a little thing on the side that I need to mention. When people ask me on the plane, because I take a bunch of flights, if there's someone sitting next to me, they usually go, "So, what do you do?" And then I have to come up with something, because in practice, I audit safety critical systems. So usually I say something like, I work in cybersecurity, because I have no idea what to say such that everyone would understand. But it's actually wrong to say that I work in security, because I don't work in security, I work in safety. And the difference is a bit blurry, and it's also, there are some arguments to be made either way. The point is that they go hand in hand. Let's give you an example. If you own a car, and your car has a car window, if I break your car window, did I break your car or did I break into your car? Right? You could argue either way. If there is no window and I get into your car, did I break your car or did I break into your car? Did I even break in at all? Right? If we send a packet over the internet, that's essentially like putting it on a flyer, giving it to the next person and say, please give it to the closest person you know that's closer to the target recipient than I am. And if we then argue you can't look at the flyer, there are some problems with that. So the difference between safety and security is blurry, but I prefer to work with safety because it turns out that in practice, things go wrong more because of people being stupid than because of people being malicious. And in these 6 hours, I'd like to talk about safety more than security. In security, you usually have this concept of a threat model where you specify what your adversary is allowed to do. Something like, they can look at every message I send that is not encrypted. This is something you allow the adversary to do, and with this model, you start to define what security means. You could do the same thing for safety. For example, it is a very strong assumption to assume that your programmers are not idiots. It would be great if we can avoid this assumption in our safety model. It is not a strong assumption to assume that every program that runs was syntactically valid. But it's great if you can make that assumption as well by using a pre-parser, for example. So it's important to know what you will allow to be wrong when you look at whether your code is safe. All right, so that's the introduction. And now I'm going to look at what it means for testing to... Oh, hold on. I missed a few parts. So suppose you're using the right tools. The first idea would be to make sure, because writing correct code is hard for humans, maybe it's not so hard for machines. So you could write a generator to write the things that are then correct because you generated them and didn't have to write them yourself. Of course, then you still have to write the generator, so you're back to square one, and now you have to be sure that the generator is correct. And, there are good uses for generators in general that's really good. Problem is you have the exact same problem. So there need to be other ways to make sure that your code is correct. So the second idea is you write the code, but then the machine checks if the code is provably correct by proving that your code is correct. Now, for the machine to prove that your code is correct, you need to know what correct means, is the first problem. Second problem is that proving stuff correct is only either it's possible in very specific cases, or you need to put in a lot of effort to make it happen. So in practice, we notice in the industry that proving is not it's not cheap enough to actually do. And then the fourth option is, the fourth thing to look at is testing, which is why I'm going to talk about testing. Testing is cheaper than proving. We can do it in practice, and it's still not done enough. I had an argument about this yesterday, about whether verification is worth it. And I said the same thing as I will say now. It would be fantastic if proving your code would be such a significant difference from what we already have that it's a big deal, as opposed to testing more. If we're ever in a situation where things are so well tested that it's worth starting to prove that they're correct, that would be fantastic. I'm out of a job that's like ideal. At the moment, we notice that even in safety critical systems, people don't test stuff enough. Simple stuff like parsing something, making it fail instead of making it throw an exception such that your entire monetary value doesn't disappear. People get this wrong, and you can fix it with a single unit test. So you don't even need to prove something to have a giant increase of value for correctness. Now, that was the introduction. So now I want to talk about when you can stop testing. When can you be all right and okay with how assured you are that whether what you wrote is correct? And I'm going to do this with an example, but I need to set up my laptop in such a way so that I can see the screen as well, because it's a bit live typing. So I'm going to have to turn around a bit. All right. So the point that I will be trying to make is that you can stop testing when the code, when any code that could have been written that passes the tests but is still wrong is less likely to be written than the correct implementation. And I'll show you that in a moment. I'll have to repeat it, I realize. All right, will I be able to see this now? If I put this down, can you still hear me? Can everyone still hear me? All right. That's the wrong button. Better? All right, I'll have to do that for myself as well. Now I'm going to write down a little piece of code as if it's something I found in my students because I used to teach this at university. So suppose you have this piece of code. How do you go about making sure that this is correct? It's a really simple piece of code, but I can talk about this exact thing for an entire hour if you want. This used to be my all-time favorite interview question. I guess now I'll have to come up with another one, but it's important enough to share, in my opinion. So we have a function here that will reverse a list, or that's the idea at least. We have an intuitive feeling of what it means for this thing to be correct, because we have an intuitive idea of what it means for a list to be the other way around. Now, what would the first step be in making sure that this is correct? Yeah, right. So let's do that. That's annoying. There we go. We already caught a problem. So what's the first thing you can do here?
Run it in Kerckhove.
Run it. I'm not in favor of running code to make sure it's correct. There is something even sooner you can do. In general, I'm not in favor of trying to run something to see if it works manually.
This should be a compiler warning, right?
Why should this be a warning?
The function is not complete,
Oh.
right?
While what you're saying is correct, this warning is turned off by default. So the first thing we can do is let's try to take a little detour. And I know this is going to be a bit basic, but you'll see why I'm going this deep in a moment. Let's suppose I have this thing called f and it is of type Boolean. How many of these are there possible? How many can you possibly write? So you can have a few of them, right? Like you can write many of these, but for the sake of simplicity, let's pretend that bottoms will be avoided in any literal code. So one of the things I want to assume in my safety model is that no engineer will write undefined and no engineer will use the function error. This is something you can enforce if you want with some linter or in code review. So let's assume that you don't use undefined and error and anything that definitely always fails. Then you have only two, right? It can be either true or false. Now, suppose I change the type a bit. Oops. How many of these f's are there? 3, right. 3 is the sum of 2 and 1. 2 for Boolean, 1 for unit. That's why we call this a sum type, right? Bear with me, this will get a lot more complicated. How many of these are there?
6.
6. Why 6? It's a product type, exactly. So there are 2 options for Boolean, and you also need an ordering. There are 3 options for that, so there are 6 total options. And now, how many of those are there?
2 to the third.
I think it's the other way around, but I can never remember either. Right.
I can't ever remember either. 2 to the third or 3 squared, right?
Yeah, it's 3 squared, I think. I can never be sure either. If there are any type theorists in the house, now's your time to shine.
It would be the number of return values for true and the number of return values times the number for false, right? So 3 times 3.
Yeah.
Okay.
Yeah.
All right. So 9 possible options. So if one of these sides would have been int, that gives you a ginormous number of functions, most of which will be wrong. Right? So it would be great if we could use types that only have one constructor everywhere. The thing is, we have complicated things to do, so we make this a bit more general. We allow for a whole number of wrong implementations. But there is a way to make sure that of all possible things that can be written, there are fewer in total, which makes it more likely that what you actually wrote is correct. So how do we do that in the reverse case? If you look at the number of implementations of this reverse function, there are many, right? There are an infinite number of lists of integers with an exponent of the infinite number of lists of integers. So there is a very large amount of wrong ways to write this function. it's not, sorry?
Instead of int, if you used like a generic type a, then
Exactly. So the problem with these ints is that you can have an implementation that looks into the int, which does something like this. Right? It's wrong, but it's something you can write. And it's not unlikely to be written, given that there is an int. So what we do instead is we make these ints type parameters. Still type checks. Now there is no way to write a reverse function that uses the concept of the contents to change the way it works. You can't say if the first element is a 0, then do something else than if it wasn't. There's just no way to write that anymore because it needs to work for any a. So the first step in making sure that your thing is correct is make it polymorphic. Now, the second step, I argue, is come up with the stupidest thing you can possibly imagine that has to be true and write a test for it. So what's the simplest thing that has to be true for a reverse function?
Empty list.
Sorry?
Empty list.
Exactly. What needs to happen to the empty list?
Is this empty?
Right. Needs to stay empty. And actually, there is no way for the polymorphic function. For a function with this type, there is no way to write a wrong implementation that still passes the test. For just the empty list. You see what I mean? Because you'd have to put something into the empty list. So this, given the type, this is not necessarily a valuable test. But you can come up with a similarly stupid thing. Oh, I don't need to use the equals thing. No. There's no way to keep this microphone in hand and type at the same time. So I'm going to write the tests here. So what else is...
One element list,
So yes, so which element?
a,
All right, so let's put an A in there. And this needs to be the same list, right? So you could start thinking about how many wrong implementations you will catch by running this test. But does it really matter which A it is?
no,
Exactly, it could be anything, right? And this is the general rule number 2. If the argument doesn't matter, make the test parametric in the argument. Right? Here is our first property test, and it came about very naturally by just replacing any argument that doesn't matter by an argument to the property test. Now you will catch a whole bunch of wrong implementations that could have been written. But there are still a bunch of wrong implementations that would pass this test and still be wrong. So the next step, I argue, is to write down the properties that you want this thing to have hold. The stupid property that well, it's not necessarily stupid because it will catch a bunch of stuff. The property that I came up with was if you reverse something twice, then it should be the original thing. There we go. Now you will catch even more wrong implementations. And now you can think about whether there is an implementation that passes the tests, is still wrong, and is more likely to be written than the correct implementation. And for likely to be written, I use the heuristic, is it shorter to write? Is there a function that is shorter to write that will pass all of these tests and is still wrong?
Identity.
Exactly, there's the identity function. So what do you do to make sure that the identity function is caught by the tests? You can write a very stupid unit test. Something like that. And now it is really hard to find, I don't think there exists a single implementation that would pass all these tests and still be wrong.
But couldn't you like just special case for that input?
No, because there are integers inside. You can do it for
Oh, right.
for three. You can do it for three things. Like if it's size 3, then do this, but otherwise do identity.
Alright.
You can still do that. But the code to do that is longer than the correct implementation. And that's what it's about.
Well, that doesn't stop people to do it.
No, absolutely. But that's where there is an assumption in the safety model that you can make, is that people will be lazy enough and use it to your advantage to guarantee safety. There are always ways to shoot yourself in the foot, and there will always be people writing stupid code. But if you can assume that they're lazy, you can use that to your advantage. So in the case of these 4 tests, where the first one isn't necessarily valuable given the type, every wrong implementation that still passes the test is less likely to be written than the correct implementation. And the first test will catch the empty case problem that we have in the implementation at the moment. All right. So at this time, I'd like to remind you of sending me pieces of code that you'd like to have tested tomorrow, I guess. And then we can start going into how to actually write unit tests and property tests, like what to type. So if anyone has any code they want to have tested, let me know. How am I for time?
Yeah, 30 minutes, I think.
All right, I'm going through this a bit quicker than I expected. So let's say we have an empty project. I called it code. You will find a bunch of stuff here, right? Usually you put your library code in your source. In your application, you put the main method and nothing else, because otherwise you cannot test it. Oh, this is an important side note, by the way. Everything you put in app cannot be tested at all, because you cannot import it. So you put nothing there.
Cannot test it with units.
Right. I mean, you can still run it, that's true. So the stack template doesn't include any HSpec code, but it does include the right file names to get started there. So in this example, I will use something called HSpec. And what we do is we add the HSpec to the test dependencies. There we go. It will start building. And then there's something I always copy paste. Oh, wrong one. That thing. And what this piece of code does is it goes through your test directory. It's just a compiler plugin. It goes through the test directory, finds everything that ends with spec.hs, and import one function from it called spec, which needs to be of type spec, which is the test suite. So we can now start writing one of those. Oops, that's the wrong button. There we go. So we have our code in this module called lib. You would probably use better naming, but you get the idea. So if the thing is called lib, then we make lib spec. We make this function called spec. It's a monad. The spec type is a monad. So this should have the empty test suite, but we need to import test.hspec. There we go, empty test suite. Congratulations. Now we spent 10 minutes not writing anything. Let's just export everything for now. This is a bad idea, but it's going to be fine for now. Oh, and of course now the application fails to build. There we go. So let's say we have this reverse function, right? And for anyone noticing that this is going to be quadratic in complexity, performance doesn't matter if what you wrote doesn't work. So make it work first, then we can talk about whether it's fast. Right, so the way you write test suite, I'm going to assume nothing when it comes to HSpec. Has anyone here used RSpec in Ruby? Yeah, so some people. It looks very similar apparently. I've never used it, but you get the idea. So what we do is we write in this monad called spec a test tree of things to test. For every grouping of tests, you use describe to describe it, and then for every test, you describe what it is supposed to do by writing it is supposed to do X. You'll see how that works. And then right after that, you can write the test. The test can be either a Boolean or an IO action that needs to be run, or a property that needs to be executed, etc. So let's write our first unit test. So what did I do wrong?
You forgot you removed name in lib, and it's also not in.
Nothing beats for calls.
Yeah, but it's exporting everything, so that shouldn't be the problem.
The main module, the main thing, doesn't contain a name. That's why it's done.
What, this you mean?
Yeah.
So I'm importing lib here, right? What's the problem then?
It's actually failing because it's.
Oh, yeah, the empty list could be any empty list. Fun. What happened? Voila. In practice, you turn on this warning that says if there is a case missing, then you should see it. The way you do that in practice is with this pedantic flag. You do need to recompile things, otherwise it doesn't do anything. Voila. And here it says you're missing a case. So you're missing a case, you write a test for it, you see it as well. So let's add the case. And now our test passes. Right? The next test we had was it does nothing with a singleton list. And that's actually a property, so we have an element, and we say that if you reverse the list of only that element, then that equals just the list of that element. And that's being tested for 100 cases. Right? So this just generates 100 things. In practice, these are going to be integers, even though I didn't specify. And then check if the reversing still works. What else did we want to do with the other property? So if it doesn't work for your sentence, you can also use specify. Specify reversing a list twice gives the original list.
Did you say it was generating 100 values to test this?
Yes, I'll show you why, proof of that in a moment. You can change this number 100 to something else as well, and I'll show you that as well. Type. For some reason now I do have to specify that this is a list of ints. No idea. Did I do something wrong?
The presenter's curse.
Sorry?
The presenter's curse. I experienced this the same.
Oh, curse, yes. Why is this? All right, so let's, oh, fun. May have to specify that it's a property. No, property is not imported. So, quick check. To dance with the compiler.
Now it's actually running 100 times.
Ah.
It's like nothing property.
So now I do have to specify that this is an int. No, this thing is unused. There we go. All right, now let's change this 100 to something else to show you. Voila, and you can see that does a bunch of these. I'm going to stop it because it's going to blow up my memory. All right.
That's when you use the quick check, right? It's
Yeah.
not like in the HPEC.
No, yeah, so HSpec runs QuickSpec. Quick check, sorry.
So if you just provide a lambda, it would run like quick check stuff.
Yes, and
Without you importing explicitly quick check.
I think you still need the property function.
Okay.
But you don't have to specify now generate all the things. You just give it a property and it will figure out, oh, it's a function, so I better supply arguments. There are some caveats, because if you write your own data type, this won't work per se. You still have to specify what it means to generate one of these. And we'll go into that in a moment. So these are unit tests and property tests. Is everyone still with me? All right. Everything still clear? Now we'll run into when you start using these in practice, you'll run into some trouble. Let me show you. Actually, yes. So a property works by generating input, supplying it, and then if something goes wrong while testing, the supplied argument is usually a lot bigger and more nonsensical than you can use to figure out what the problem was. So what QuickCheck does is it tries to shrink the thing that made the test fail to something smaller that still makes the test fail, so that you get something more sensible. So let me give you an example of that. I have this feeling, which is wrong, but that's another story, to upper, that if you uppercase a character, then it becomes uppercase. Right? This feels true to me. So we'll have a check that. Oh, I need to import data.car. What else did I do wrong?
You need the property again?
Yeah, oh yeah, good point. What else? Oh, right, I need to say, specify if you uppercase all characters of a list, then the entire list becomes uppercase. All right, and we see a counterexample. It's the list of 1. So what QuickCheck did was generate a certain list. It found out that this property is actually false, and then it made the case smaller such that we can figure out what the problem was. If you disable the shrinking, like so, then you get a much more complicated expression, I think. It will depend a bit on the randomness. So the for all function is used to supply your own generator. The arbitrary generator is the default one to be used. So this has the same workings, except the shrinking is now turned off because of reasons that I will talk about in a moment. So if I actually be a bit annoying about this, if I'm actually a bit annoying about this and uses larger size, you'll see what the problem is. So in practice, you'll see something like this. Like this string does not satisfy your property. Figure out why, right? So that's why QuickCheck tries to shrink this input to something that still fails, but is now smaller and easier to reason about. And it uses the shrinking function for that. A shrinking function is just a thing that takes, just a function that takes a thing and produces a list of smaller things. And ideally, it starts with the smallest first. So I turned off shrinking on purpose, and the reason is if you use your own shrinking, if you use your own generating function, then shrinking starts to break very quickly. So let's say that I use the property. Let's leave that. Oh no, it needs to go. Every number greater than 5 is even. So I need to generate numbers that are greater than 5. All right? So I can use if I try to use this, and I say for every number it's greater than 5 and it's even, that's not the thing I'm trying to test. What I'm trying to test is that every number greater than 5 is greater than 5 and even. So I need to change the generator such that it will only generate numbers that are actually greater than 5. And there is a function for that. It's called such that. There we go. So now, the idea here is, what did I do wrong again? Okay, I'll do that in a moment. So the such that function takes a generator, for example, arbitrary generate anything, and then applies a predicate to the thing that's being generated. If the thing that's just been generated satisfies the predicate, then it will be returned, so generated. Otherwise, it will just try again. So what will happen here is that QuickCheck will generate a random number. It will check if that random number is greater than 5. If it's not, it tries again. Now we need to make sure that this compiles to show you what the problem is with this thing. Oh, it's a property thing again, isn't it? No, that's not it. Wrong buttons. Now what did I do wrong here? I really need to specify that this is an int. Apparently, yes. So if you've never done this before, then the following, and you don't turn off shrinking for your own generators, that's like so. So you use a custom generator and a shrinker. The default shrinker is just called shrink. Then you'll get some weird outputs. So if you look at this output, you may think that this says, oh, your property that every number greater than 5 is even doesn't hold, because here is a number that's greater than 5 and not even, namely 0. So you need to make sure that if you use a custom generator, that you also adapt your custom shrinking function so that the invariants that you maintain with your generator are still maintained by your shrinking function as well. or you turn off shrinking entirely. So the correct shrinking function here would be filter out all the things that are smaller than 5 after shrink. Like so. And now it will say, oh, here's a number that's greater than 5 and not even. All right? So make sure that the invariants that you maintain with your generator are also maintained by your shrinking function. How much time do I have?
Like 3 minutes.
All right, then I'll stop here for now, but you had a question, go on.
Yeah, how does the such line work? Does it only generate 100 test cases, or does it give up after trying to generate 100 tests?
That depends on the settings you use. I think it will still do 100 test cases, but if it generates something that doesn't satisfy the predicate, it will try again as opposed to just skipping the test.
Yeah.
So it's quite important that you know about this, because if you use an expensive predicate, or if you use something where the generator doesn't generate a lot of things that satisfy the predicate, then you could be waiting a long time. And in practice, we noticed that if a test suite takes long with property tests, it's not because the tests are slow, but because you don't generate the right values quickly enough. So when you do use such that, make sure that you don't have expensive predicates, or that most of the things that you generate are going to satisfy the predicate. The other way to do this is to generate an arbitrary value, apply absolute value so that it's definitely positive, and then add 5, and then every value that you generate is going to be greater than 5. Then you don't have to check this every time. Maybe expensive as well. Then there's the middle way where you do the absolute value, apply it to the arbitrarily generated thing, and then check if it's greater than 5. That's more likely to pass through the predicate than the other one. All right, I'll stop here for now. This was the small introduction to why you would do testing and how you type it. Literally, which buttons you press. If there are any more questions, let me know. Let me know if you have any code that you would want me to test so that I can start preparing for it. All right?
Where can we send that to?
Just tell me. All right, so I don't have a microphone anymore. I may have broken it. Sorry? It's recorded. You will be able to hear me, but just not live. All right, did everyone who tried to replicate what I just did manage to do it? No more weird issues? All right, cool. We blasted through, well, yeah, I talked about everything I wanted to talk about in 2 hours, so I'm going to steal some material from tomorrow and talk about how to do property testing in practice and what kind of issues you run into and how it works on a real project instead of reversing integers. So I'm going to steal some information from a talk I've already given, which will be online, but I'll dig into some of the more practical examples instead of just talking about them, and then you can see how to do certain things from scratch. So I've talked about testing and property testing already. Now I'm going to dig into property testing specifically and what kind of issues you might have. So we've seen what property tests are. You generate an argument, you check that the argument satisfies the test. If all of the arguments for about 100 test cases satisfy the test, then we say the test passed. If one of them fails the test, then the test fails. I'm going to skip through a bunch of these slides. Right, so the first thing I'm going to dig into is how a generator works. Generating values happens with this thing called a generator. A generator has one type argument, which is the thing that it's going to be generating. A generator uses 2 things. There's, on the one hand, the seed to make sure that the random generation stays deterministic, so you can run it in pure code. And the second is called the size, which guides the generation of values that can have a different size. So when generating an integer, you can imagine just picking an integer from the entire range of possible integers. But when generating a list that can be arbitrarily large, you don't really know what kind of size of a list you should be generating. Should it be 100 elements or 10,000 or 10 million elements? There's no real way to know. So QuickCheck uses this size parameter for the generators to allow to control how large the lists are going to be. And then it chooses elements starting from size 1 to 30, I think. I'm not sure about these details. Generates an argument of those for 100 cases, and then shrinks back down if anything fails. So that's the second thing, is shrinking. So if a property test fails, I've just showed you this example, you get something incomprehensible. So QuickCheck tries to shrink this value to something smaller that still fails the test. In this case, if you turn shrinking back on, you get this simple counterexample 1 after a single shrink right there. All right, so then we can see that if you uppercase a 1, then it's still not uppercase, so this property doesn't hold. So how are we going to write generators? We have some building blocks that are built into QuickCheck, and they're really all you will need. There is a type class called arbitrary, which a lot of the basic types already instantiate, which allow for this single generator called arbitrary, which can generate any one of those. So arbitrary is the generators for int, for example. And now we're going to go into some practical details. If you want to test your generators, is this readable? If I have QuickCheck in scope, then I need to make sure it's possible. I'm going to do something blasphemous and just add it here. Oh, actually, no, I'm not going to do that. There we go. Now I should have QuickCheck in scope. No, maybe not. Now I should have QuickCheck in scope. Yep, there it is. So arbitrary can generate arbitrary things that instantiate the arbitrary type class. The way you figure out whether your generator does something sensible is with the sample function, which takes a generator and prints a few of them. So sample arbitrary integers. We'll show you some integers. Same thing for characters. Same for strings, etc. So this is the way I will be able to show you some generators. Then there are some building blocks. The first building block, let me make this a bit smaller so it fits on the screen as well. There we go. First building block that we already talked about is called such that. So I can make an arbitrary integer such that it's positive, for example. I need to make it integers. Voila. And now this will only generate positive integers. So let me reiterate. The way the such that thing works is you generate a thing, you check if the predicate holds. If it does hold, you return it. If it doesn't, you try again. That means you can make it be really slow if you do something like this. Generate an arbitrary integer and only let it through if it's 100. Oh, I guess it's not that slow. There we go. This is rather slower. If I add another 0, this will take ages. You get the idea.
And this arbitrary type class is defined for all the usual data types?
Yeah, but nothing you've written yourself, of course. So the way you write this such that equals 100 is by writing pure 100 because generator is an applicative. There we go. And then it goes rather quickly. The third building block is called elements, which generates a uniformly random distribution over the list of elements that you've supplied. So if I use as my generator elements 1, 3, 7, then it will only generate, come on, where's my bracket? There it is. Only 1, 3s, and 7s. Right? So here's another example in the slide presentation. If you have generators for suits and generators for values, then you can generate a card by generating first a suit and then a value. It's also a monad, so you can, for example, generate an arbitrary number, and then generate that many cards to have a list of cards. All right, still with me on the generators? Any questions on the generators? So if you know how a do notation works, you'll be fine with generators. The second half of the generator is the size. And sometimes you want to have some sort of control over the size, and I'll show you why in a moment. There are two ways you can control the size. The first is called sized, which is where you supply a function that uses the size and make a generator out of it. And the second one is called resize, which is where you set the size of the generator that you're going to be using. So here's an example. If you want to generate a list of 15 ints, there is a convoluted way to do it with these two building blocks. First, you set the size to be 15, and then you say we're going to use the size. The size is n, and then we're going to generate 15 of these ints. All right? The size of the int that will be generated in this arbitrary will also be 15. So every integer that's generated by this arbitrary will be using this 15 as well. And then I just told you about, sorry?
What do you mean by using 15? Do you mean it will be 15?
No, it will be less than 15, I guess. But it's up to the implementer of the arbitrary instance to decide how that works. The problems with such that I've already talked about, so equals 100 instead of just pure 100 will take a long time. So you need to watch out for predicates that are expensive or predicates that are rarely satisfied. For the sizes, there are problems if you use the size, if the property you're trying to test has anything to do.
Difficult for microphone?
Yes, I don't know who has the microphone.
Where is the microphone?
They took it with them.
What?
Someone took it with them when they went to see if it could be charged.
But when is the microphone?
When is what?
Where is microphone?
Oh, no idea. I don't know. Someone took it with them.
You don't.
I don't have it. It was Michał.
Nie, bo myślałem, że jest jakiś problem z mikrofonem. Dostałem taką informację. Halo?
So you'll run into problems when the property you're trying to test depends on the size of the generator that you've used. Whether the property test succeeds depends on the size of the generator. For example, you can test a property that checks if all lists are smaller than 100 elements, and QuickCheck will say yes, of course, because there are no lists larger than 100 elements. At least if you generate them with the default settings, because QuickCheck uses sizes up to 30 by default. So if you do the resizing, then it will be able to falsify this property. So watch out for properties that depends on the size of the input. There are some more dangers with size, and it's when the size of the thing you generate depends non-linearly on the input size that QuickCheck has as the parameter. Let me show you an example. Suppose you wanted to implement the arbitrary instance for trees, then you can say one of, which just takes a list of generators and chooses one of them. One of a list of 2 elements, where the first one is just return a leaf, and the second one is return a branch, and then 2 more trees underneath that. The problem here is that, well, let's define the size of these things first. The size of a tree is the total number of things in the tree. The problem is when you generate a tree of size 1, it can be arbitrarily large, because it can either generate a leaf, and that's size 1, or it can generate a branch and then try again twice. So these sizes could be enormous, and they don't depend on the size at all, the size parameter at all. So the way you would do this, the problem with this is that you will run out of memory while running your test suite. So the way you fix this is by writing a custom way to use the sizes. And the way you do that is if the size parameter is smaller than or equal to 1, then return a leaf. Otherwise, split up the size parameter into two numbers that sum to the size, and then generate subtrees with those sizes. Actually, I should have done n-1, but that's not a big deal, actually. Okay, so everyone is still with me when it comes to how you write property tests. Are there any problems with that? Because if there are, now is the time, because I'm going to go into the more cheaper ways to write property tests. All right. Yeah, you can write cheaper properties.
Okay.
I'll do that and that. All right. So it could be that you write the same property a bunch of times. For example, for both less than or equal to and greater than or equal to, you want to check that this thing is reflexive. So it's always is satisfied when you compare something with itself. Then you could have written these two properties. The should be function is just like equals equals, except it's in IO. Long story. But you can read it. So you can abstract over this and write a property combinator, as we say. That's where you have a function that produces a property from something else than just the entire property. So in this case, you supply a function, which is a binary relation. And you generate a property that checks that if you apply an element to itself with this relation, then the results should be true. And then you can rewrite the code like that, and you can have some cheaper properties. Still with me? Now, suppose you want to do this for the entire ORD instance. You still have to write this entire tree again for every ORD instance. So you can actually do something way cooler, and this is by far my favorite part. Well, hold on, here are some more examples of property combinators. You probably would have written them yourself, but they exist. I will show you them tomorrow. This is the next part. I love this part. So what happens here is that you can generate an entire test suite as a combinator as well, instead of just one property. And in this case, I want to write a test suite that checks all of the things I care about in an equality instance for a given type. And so it's a bit more complicated than the type that is here. But this will show you how it works. So what happens here is that for any arbitrary A, you can generate a test suite, as long as the A can be generated by randomness. Now you'll notice that this A doesn't show up in the type of test suite, which is called spec. So you need some extensions. The first one is scope type variables, so that you can talk about the A. And then you need this A dot explicitly. And the second one is allow ambiguous types. This allows you to write that in such a way that the A doesn't appear in the test suite type. And then you can implement this. It's about 100 lines long, so I'm not going to show you that. You can write an entire test suite like that. You can just say, test that equality makes sense for integers. And then you get an output like this. And it will just test all of these properties. And you can reuse that in a single line for all of the types you have written your custom equality instance for. There are similar ways to do this for ORD, for monoid, for monad, for applicative, because you cannot just do this for, you can also do this for non-symbol kind of types, like lists, for example. You can say monad spec at list, and it will check all the monad laws for your list. So these are what we call test suite combinators. We use them a lot in practice.
And arbitrary must be or must also belong to EQ type class, or?
Well, yes. So I omitted some things here. There's EQ and show and typable and data, and like there are some more constraints.
Arbitrary in itself, it does not require. Does it require?
No, it doesn't. No, it's just type class without assumptions. But in practice here, you will need show to show error messages, and you'll need eq to check things. And there are more constraints than this, but it didn't fit on my slide. And then I'm going to go into some more of these. But first, this also exists for example, JSON serialization. So you can have JSON spec at my type, and it will check the round trip properties, and it will check that you can't supply something that should have been wrong. And there are really convoluted test suites that you don't have to write anymore just because this exists already. And I'll talk about that more tomorrow, because apparently if you use this with just quick check, a lot of things will go wrong. So I'll tell you about that tomorrow. But now I'm going to go into some more practical examples of how we use properties, because I'm assuming that to make money you won't write reverse functions. You will do something like write a web service and use a database, right? So now I'm going to talk about how you can use property tests when you've got a database that is being looked into by a web service and then exposes some API. So the plan is, before you start running any tests, you set up the application and the database. For every test, you use this database, and you can share the state between the tests, so make sure you know about that. And then at the end, just delete the database again. And you can do this in all of this in HSpec without doing any manual steps. So the first thing we're going to do is we're going to write a function called setupMyApp that produces an HTTP manager, which is the thing that you're going to use to call the web service, and a Y application, which is the thing you run to supply to serve the web service. And then you can write this function, which is a bit complicated to explain. It will use the manager you've just made and the application you've just made. And it will take a test. And this test will have access to a client environment which contains everything you need to know to call your API. And given one of these tests and one of these tuples, we will now actually do the running of the test. And the way you do that is by using the warp test with application function. Warp actually has support for this exact case, where you just supply the application and then make the client environment and put it into the test and see what happens. All right? Still with me?
So the environment is just port?
The environment is just what, sorry?
It's just what? It's just port?
Oh, no, this is the environment. Client environment, which has the HTTP manager to connect, and then the base URL, which contains the where you need to go looking for the web service. Now, what this client environment contains doesn't necessarily matter, but it will always contain a port at least. So it could be that there's more in there, but it doesn't. This is just an example. Everyone still with me? All right. Now, this test tree that you make in HSpec by default makes tests that need nothing. But you can tell HSpec that this part of your test tree needs an argument. And the way you do that is by making something of type spec with a client environment, and I'll show you in a moment. Then the tests have access to this client environment and whatever happened to set that up. So the way you say what you do here is before any tests are being run in this subtree, set up my application. For every test, you can run it with this client environment that I'm going to make of what just came out of the setup my application function. And at the end, we clean up the database. All right? So this is a test suite combinator that turns a test suite that uses a client environment for every test into a test suite that doesn't, so that you can use it in your tests. And then you can write something like this, and I'll go through it one by one. So this is the entire test that you may want to write to, for example, test that this call my API function is idempotent. Is that right? Yeah. So let's say you have a helper function that uses the client environment that you get from your test framework, assuming you have it, and this client M thing that actually does the calling and make an IO. And you have another function that uses an argument and does something in the client monad. Then you can write something like run a client function with this client environment that I will have gotten, call my API twice with the same argument, return the results, and then check if they're equal. Make sense? All right. Then where does this argument come from? Well, it doesn't matter what the argument is, so let's make a property test. We just say for any arbitrary argument, this should hold. And then we still haven't got this client environment. So because we just wrote this helper combinator, we can now assume that it comes out of this it. So this client environment will come out of the it, and we can start using it. And then this entire describe expression is now of type spec with a client environment, because that's what you got out of the it. So we need to explain to HSpec how to get this client environment and put it into the tests. And that's with my server combinator that we just wrote. And this is then a test suite that doesn't need any arguments anymore, so we can just use it as the test suite. All right? So this is what you do to write property tests for a web service that uses a database. It does share state. If you don't want it to share state, then you have to either reset up the database every time or clear it. I usually don't, because most of the time I work with applications that has users. and then you can just generate a new random user so that the state for the user doesn't clash anyway. All right? Everyone still with me? Then there are some links to relevant projects that I will talk about all of them tomorrow as well. So there is QuickCheck, which is the property testing framework. There is HSpec, which is the testing framework that I've been talking about today. Then there's Validity, which contains a lot of these pre-prepared property combinators and testing combinators. The first hour tomorrow will be about Validity. It's about how you can make even cheaper property tests. And then I'll also talk about some recent research that makes property testing in general even cheaper. The biggest problem is that when you're writing property tests, now you solve the problem that you don't have to come up with all the examples anymore, but now you have to come up with these generalized mathematical properties of what your code does. And that's not just hard, but it's hard to come up with, it's annoying to have to come up with these things, especially if management says like, you need to make this work, and they're like, I don't know what this needs to do. So you still have to come up with the properties. And QuickSpec tries to solve this by, while you're writing your code, you can run QuickSpec, and then it will say, hey, is this what you tried to do? And it will suggest the test to you. So you can just copy paste the test if you think like, oh yeah, that is exactly what I wanted to do. And then you copy paste it in your test suite, you keep it there, and you make sure it works. And then there are some problems with QuickSpec that EasySpec tries to solve, and we'll talk about those later as well. But that's as far as I've gotten for the theory of this hour. How much time do I have? Maybe I can go through the actual web application as well.
So you have 15 minutes?
I have 15 minutes. Sorry? 20. I'm thinking whether I can do the web server thing. Yeah, I'm at a good stopping point here. Yeah. All right. So that was practical property testing in the second hour. Tomorrow I'll start doing the live testing, and I will also talk about cheaper property testing as well. So if you have any more things you want to test, send it to me. I'll put my email up for a while until the next speaker is here, and then I'll see you guys tomorrow.